So let's continue. Now I'm going to leave the implications of statistical hypothesis testing and go on with prediction and validation. And the first thing is there are many packages out there doing different tasks for the prediction and validation. And this is a cheat sheet for scikit-learn, and you can see here the decision tree, which methods you should work with, and well, from that you can probably look at yourself, but generally you can see here that one decision here is, do you have labeled data, yes or no? If you don't have labeled data, you go to something in the direction of k-means. If you have labeled data, you can, for example, go to something in the likeness of k neighbors classifiers, etc. Also, one message is if you have less than 50 samples, then in principle you should get more data. And there are also cases that scikit-learn doesn't handle, so then they just point you to tough luck. You have to find something else. I'm not going too much more into this, but it can be helpful for you to select your method. And now I need to convince this one again. Let's see if it works. So what we have a lot of functions that map the inputs of your data into some kind of output conclusion. And the input could be different information. It could be a full image, it could be a point, it could be some feature vector, for example, different shape parameters. It can also be a multi-dimensional tensor, for example, a spectrum or something like that. And the output is of very reduced form. So it could be a single value, so a regression result, could be a class assigned with that. Then you talk about classification or some kind of grouping. And it can also be some vector matrix with fewer degrees of input than the original data. So you get some kind of dimensionality reduction of your data. A problem is often that you do overfitting if you have too little data or too specified data. So here we have an example of a magic classifier that you train with these three categories. And when you test it, you see, well, that's good. If you test it on the same input, then you get the exact same results. On new data, it doesn't work so well, maybe. In this case, we were lucky. It seems like we get octopus is an animal. That's good. Dan is a person. Also good, fantastic. But maybe this magic classifier, based on the information we have, it probably only took line 1, said, okay, first check is an animal, second check is a person. And that's not really a good one. So it's the risk is, and something you have to watch out for when you do this training, is that you're not getting too specified to the kind of data that you actually have. And otherwise, you will get very strange results when you try to apply it on unknown data. So that's why we need to have a good training. We also need to validate the training while doing it. And finally, test it again on a testing data set. So this is that we need to do. We develop with training data, and then the iterating validation on a validation data set. And yeah, there is the testing in the end. So we have also the difference between qualitative and quantitative information. With the qualitative, we get information back from visual feedback, for example. We can also, by experience, compare different expectations. And qualitative information is a good starting point because you get an idea where to go. But in the end, you really want to quantify it to get numbers to make your conclusions correct. And then we get to the quantitative metric. So then we start measuring things like shapes or distributions of different shape metrics. And with that, we can also establish, and that's the important thing with the quantitative, that we can establish the relationship between some kind of changed parameter in your experiment and a metric that you can read out from the images. And this one should work, I hope. That one. Yes, it works. So we have this algorithm, which is essentially a combination of a Gaussian filter and a thresholding. And the output we want to use for one thing is the thickness analysis of some objects. And the other thing is the shape analysis. And in this algorithm, we have different parameters. We have the raw data that comes in, and out comes some kind of results. Then we have three different parameters. We have the sigma of the Gauss filter. We can also say which neighborhood we have. And so that are the two parameters controlling the filter. And then we have also a threshold level to set where the limit is to decide if it's an object or not. And now we want to see how that can affect the results. And for example, if you run a parameter sweep on different threshold values, then we can see that the output in volume varies with different threshold level. As I actually think it's quite interesting that you get a dip, but it looks like you have some rather constant level up to 4,000, and then it goes down more towards the 8,000. So there is some connection, and then you can see also from this kind of scan what is the effect of different thresholds on the output metric. It's a little bit related actually to the ROC curve, but this is pulling it all the way through the analysis. Because in the ROC curve, you only have the direct connection between your detection variable and the threshold level. Here, you really have the connection between the threshold and the final result. You can always look at it in different ways. So here is using a Violin plot where you can see that most of the values, they're actually focused around the lower volumes, but there are some outliers. That's a bit harder to see from this scatter plot that you have here. But there's also different values I'm looking at here, by the way. It's the volume, and here is the orientation. So it seems like we have a trend in orientation that is a little bit biased above 0. Yes. A Violin plot. Yeah. What it does, it is on one side, it's kind of histogram in categories. So what you see here is one is the spread. So that would be the bins in the histogram, and the width is the number of counts in the histogram. And that you can set then for different categories. Like in this case, it was for 2,000, 3,000, 4,000, etc. And sometimes it actually looks like a violin. Other cases, it's just a little blob in the middle, depending on what it looks like. So that is a way to compare many different histograms instead of just plotting them on top of each other, if they have different clear categories. What we also want to know is how sensitive our system is to changes in the parameters. And in control system, when you maybe just talking about having an input voltage to an output voltage, then you can just do a change in the metric. No, a change in the parameter gives a direct change in the metric, and it's unitless. But in image processing, it's a bit harder to do that and still letting it making sense. So, for example, the threshold is in image intensity, so it's some gray level, but the output metric is maybe volume, and that would be the unit would be cubic meter. And well, then the unit would be volume per intensity, which doesn't really make much sense. So what we can do instead is to measure, for example, the sensitivity as the difference between the min and max divided by the average, and then we can see what the output is for different levels. And here is an example where we look at the object count for different thresholds, and we can see that in the beginning there are very many objects, and then it goes down to a minimum, and then it goes up again. So that gives us kind of a sweet spot for the object size with the thresholds. Actually, I'm a bit puzzled that this curve actually looks like this, but this comes from real data. So because if you have a very high threshold compared to a very low threshold, yeah, I'm puzzled about the shape of it actually, but because I would expect merging with the lower threshold and more splitting up at the higher threshold. And then you can test this against different parameters, and you can see that in some cases you have the sensitivity going down for one, so that would be the count, while the volume and anisotropy actually goes up. So it looks a bit contradictory, but then you have to decide if it's what you're looking for, which feature you actually want to tune for. And then we check on, we go to reproducibility. So it's important that if you have an algorithm, it shouldn't be sensitive to measurement conditions. So for example, how you mounted it or rotated the setup shouldn't be sensitive to noise, or also ideally not depending on exact illumination. Some cases it's easiest to do it that way, but if you can take out the dependence on illumination, that's good. For the analysis part, you shouldn't have any platform dependence, so it should run the same way on a Raspberry Pi, for example, and some kind of cluster supercomputer. It shouldn't be a difference in how the output is. There shouldn't be, well, that's more a choice actually, but there shouldn't be too many proprietary or in-house algorithms, because they are usually not so well documented. So I'm actually promoting open source generally for the analysis. In particular, if you have published your data, you should also make the code available for your work, making it possible for other ones to also reproduce what you have done. Also, try to avoid too much manual clicking or tweaking, or also actually manual copying tasks in your process, because that, for one thing, it's not fun to do it. You have to spend quite much time to do the manual clicking and copying. So if you can turn all that tasks into a script, that's ideal. And your recipe, as I said in the beginning, should be several steps, but for your complete analysis, you should have some kind of overall script that actually executes your recipe step by step in a long row. to get the results. That saves also time if you need to change something, or if you get new data, makes the work much easier. And you can do the same thing every time. If you want to do some analysis, here are some ways of how you can run different scripts. In Python, in particular on Linux, Unix-based systems, you can actually run the script, a Python script, directly from the command line, and that would, in that case, include this shebang part, telling which kind of interpreter you want to use. In this case, we are using Python, but you can also use it for Bash or whatever kind of shell script you're using. Then comes the Python script that does something, and the script sets up which file, which threshold you want to use, and then it calls the script that actually does the routine. In MATLAB, ImageJ, or R, you have a little bit different approaches. So you can run in MATLAB, I think you need to write a little script that calls MATLAB with different input parameters. With ImageJ, you need to run the ImageJ runtime and then add some macro and the images. So there are different ways of calling your scripts on from the controlling script. And in R, honestly, I'm not using R very much, so I don't know really how this parameter works. But if someone of you are doing it, then it's also a possibility to run that within a bigger control script. So now I'm switching topic to data frames. You have seen during the lectures sometimes that I'm using something called data frame, and data frame is kind of a database where you can have different categories and you have many measurements, and it's a very convenient way to work with the data in your analysis, because from the data frames you can compute statistics, you can sort out different parameters or categories. You can also do plotting directly from the data frames. And the most frequently one in that we have been working with is called pandas. And your workflow looks something like you have done your measurements, you do some processing using Python, and then you need to store some information that you get out of the analysis, either in some spreadsheets, database, online or locally. And then finally, you get some data out that you want to look at. And we have different ways of doing it. In Python, the easiest or the very simple way is to use arrays, one array per feature. You can also work with data structures or dictionaries in Python. And what you want to do on this feature data is, one is counting. That's a very simple one. You want to compute statistics, if it's the average value, standard deviation, median, etc. Maybe you want to do some transforms, so do some calculations on the data, rescaling or something. And finally, you also want to visualize the results. The problem is with these very custom alternatives using arrays, it's quite time consuming to first think up a structure you want to use, and also how to then afterwards analyze the data. Because during the image analysis, you may use some structure which is efficient for the for the data extraction, but that structure may not really be what you need when you finally do the statistical analysis or plotting. And it's very easy to do the wrong things, and sometimes you get stuck in a dead end just due to wrong organization of the data. And what Dataframes helps you with is, it's a container, essentially. It's a huge array. which is organized into columns and rows. And it's very much like a spreadsheet. And you can actually also load in spreadsheet data from Excel or CSV files. And it takes data in the columns. And with that, you can easily do filters for selecting different categories. You can sort the data from the rows. You can perform some arithmetics, creating new columns very easily. And then you have the connection to where to store and read the data from. There are quite some resources using, for example, pandas. There is the main pandas documentation and getting started with pandas. And these are actually pretty good go-to places if you want to work with pandas. I think it's pretty easy to get started using this information. So the first thing is how we create a data frame. So I already said we start out with some arrays or dictionaries and in our data storage. And actually that's a starting point also for the data frame that we take, for example, format it as a dictionary, or we can take it from a data file or NumPy arrays. Depending where you take it from, you have to do a little more decoration. So a dictionary is easy because then you already have the column names given by the dictionary. Data file depends on where you get it from and how it's formatted. The NumPy arrays, then you just get a bunch of columns, but they're not labeled, so that you have to do afterwards. And to get pandas in, the typical import is just import pandas, and PD, I think, is more or less the standardized abbreviation for pandas. And here you can see an example where I load the data from this phenotables CSV. Is a comma separated value. And I see from the path that I actually yesterday evening changed the path. They are not located here anymore. It's 8. So that needs to be changed in the slides. But anyway, the data is the same. So when we read it, we get this many informations. I think this is some bone data with different phenotypes and exactly the contents. I, to be honest, don't know, but you can see at least here is a selection. So we read CSV. It could be also read Excel, and then you have to specify which sub sheet it is. And the next line, I'm looking at it, and it's here is the name of the data frame is pheno.sample5, means it takes 5 random sample rows from this data table. 2 other ways of displaying the contents is to do head. Just takes the, I think by default, it takes the first 5, but you can also specify how many lines you want from this table. And saving works the same way. Then you can do to CSV, and then it writes out the new CSV file. And if you want to create your data, you can do it using dictionaries. So in this case, I'm creating just a little list here of dictionaries. So here I have position label equal to I, and the sign is equal to this. This may not be the most efficient way, because here I actually recreate small dictionaries, and you can wrap it around the other way, which I think I show on the next slide. And then once you have this, you go on and say you want to create a data frame. So that would be PD data frame. And then you take this list. And afterwards, you can see here the values. Again, I took the randomized output. The alternative way is actually to create only 2 entries and add 2 NumPy arrays and then store that, and the result is the same. Only difference is here I use the head command and then I get the first 5 rows of this table. And now that we have this first table, we want to work with it and do something more. And the thing is, you may often want to add a column with new information. And adding a column is very easy because you just, when you have a data frame, you just write the name of the new column and set it equal to some either something new data or something based on a previous column. So in this case, I compute the cosine, which is the cosine of column position. Then I create a new column, sum, which is the sum of 2 columns. And then finally, I also have a selector, which says if it's positive, and then I check if the sign column is greater than 0, and then I get the final table with the cosine, sum, and positive, and you can see the results here. And also it writes out, this is a Boolean variable, then it writes out true or false, not 1 or 0. And in these columns, in this table, you can also filter out information. And this is where it gets really powerful because you can, for example, sort, create a new data frame, which only contains all the values where the column sign is above 0. And then you get a separate data frame where you have this selection. And that's very useful if you, for example, have different categories. Then you can use this to have extract only a specific category. If you want to make statistics of, for example, only cats, if you have a different animal table, say, if it's equal to cats, then I want to do something. You can also okay, this is, yeah, that's a repeat of the other one. So that one I can skip. You can also rename the columns. So if you are not happy with the column names A, B, then you can rename it that columns A becomes hay and B becomes hop. That's also possible. So if your first category names were not ideal, or if the data as a table from someone else and you want to name it more conveniently, then you can do this. Interesting things are also to compute the statistics of the data. And here I show the example, only computing the mean value of the whole data frame. And when I compute it like this, I get a list of all the averages. Interesting is that the Boolean actually now turns into a number, because then it's the average of 1s and 0s. And do that also column-wise, or you can even, if you don't want to do it for each, then you can also use df describe, and then you get a lot of information. You get how many, you get average, deviation, minimum, maximum, and the different quantiles. And this, of course, also now, as I already hinted on, also works on specific columns and with filtering. So here I make a little very detailed example where I filter all where the sum is greater than 0, and then I want to look at the standard deviation of the sine curve. And maybe it doesn't make much sense mathematically, but this is the kind of filtering you can do with your data. when you come to your own data, you can make such things that actually make sense too. And another way you can do is you can use grouping, and you can say you want to group your data by some category. So you have the group positive, which was just checking if the sign was positive. Then you can say you want to compute the average of category group positive, and then it computes the averages for true and false separated. And the output of that line becomes like this. It's a bit cluttered, and with some pandas magic, a couple of extra lines of details, then you finally can get it into, you only get the average of false and average of true as a small little table. That is maybe a very detailed example how you can do it, but yeah, maybe useful for you. Another thing is, if you have a lot of data points, it's always interesting to plot it. And you can actually plot directly using Matplotlib, as we have done before, but you can also just use the plot commands, which are linked to Matplotlib, for the data frames. So you can do data frame plot, and you can tell also which axis you want to plot in, and then you get a plot of all data frames. As you can see, it maybe doesn't make sense because the position here is not really very useful. It's just a straight line. So that one you could filter out. And with that, we can now looking at different columns. For example, here I'm plotting only the sign. And here I'm plotting the X and Y. So I say the X coordinate is given by the sign column and the Y coordinate is given by the cosine column. And then we get a circle, which would be expected. Then we can also do the filtering as I've done before. And here we have X equal to position and Y is the cosine. So you can do different ways of presentation here. Different plot styles. Now, before I just used the normal plotting, drawing a line between the points, but you can also do bar plots or scatter plots, depending on what you need to do with your data. And that you decide using this kind, and then you set how it should be represented. And then when you get into more advanced, I think actually I skipped this part, but you can merge different data together. If you have several data frames, there's examples I skip because otherwise I can't fill in the time. So when are data frames useful? So pandas is useful for large data. That means as long as it fits in your computer, the local memory, it's fine. If you really want to use big data, then you need to think about other data frames. So for example, Dask provide data frames with the exact same interface. So you can just switch DF to Dask DF, and then you have the same. And how can we bring in our data? Which information should be stored? You can actually store your volume data in a data frame. That's possible, but I would probably not do it because it's not a convenient way to work with. In particular, also if each image is several gigabytes large, you soon fill up your memory with that. But I think when you increase the level of abstraction, when you come to feature data, then it starts getting relevant because then you may have only some thousand, maybe 100,000 items with different features. When you come to statistics, sure, why not? And model, possibly, yeah, depending on what the model is doing. But yeah, images, I would be doubting about putting in if they are really large. Some cases, for example, in the machine learning cases, the dogs and cats databases, I think they were pressed into a data frame. So last part for today is about presenting your results and getting your result out. And the reason to visualize your data is very different. So for one thing, it's maybe about discussions. You have done your experiment. You want to maybe discuss with your colleagues, see how to work on with it. Then you present your data in a very different way than you would do if you present it in a presentation on a conference or even in a publication. Because the data you visualize in the discussion is very detailed and probably cluttered with too many details that's maybe just confusing for the viewers of the different other alternatives. So one reason of visualizing the data is that first, tables are not very easy to interpret and see patterns in. And 3D visualizations are also usually not so easy to compare visually. Some cases, of course, obvious, but other cases, it's very hard. And often you want to see very specific things, and otherwise, in our cases, you want to look at the large data set to see trends and find problems in your work. So the purpose of the visualization is you have to define the reason. So one is understanding and exploration. Then you have often a very small and known audience. The audience also have a very high degree of understanding on this specific topic. I realize there is formatting error here. And the other one is presenting your results. Then the audience are often very much wider. And you don't always know the audience. Could be a reader of a paper or person listening to your presentation. And at the best, they usually have just a general understanding of the topic. The other thing is in what kind of media you are presenting. If you have a live presentation or a written document or email, if you have the live presentation, you can have very much control of how the data is presented. You have interaction with the people in front of you. So then you don't need much detail because that's just confusing. On the other hand, if you do it in the written form or in an email, then you have to have very high level of detail because you have to leave the whole interpretation to the observer. Because you don't have any control of how to work with the data, or how to interpret the information. Then, of course, there are very many bad graphs. Very many graphs say, my data is complicated. Great. Or else the graph tells you, I know how to use this fancy toolbox in MATLAB, Python, Mathematica, whatever. They are overly fancy. And another problem is that most of these programs for visualizing the data, they actually make pretty poor plots in the raw format. And it's actually quite time consuming to produce a plot that works well to explain your point. XKCD is always good at capturing things like that. So he is making fun of the PowerPoint MS Paint area in the presentations. And actually, there is some truth in it. I think many of the Excel graphs that are produced, they are horrible, to put it simply. It needs a lot of post-processing to get the raw plots that you get out of those software in a decent format. So here are some bad examples. Actually, it's getting even worse with this Beamer. But anyway, in this one, you have some kind of scatter plot. And in it, there are some red dots, which are hidden. You don't see them. Another one is this one, which is, in the beginning, you can see some separation between the different graphs. But at the end, there's just a big fog of points, and you can't make any conclusion out of it. So please avoid that. There are much better ways. So if you need to do that, please ask me. Then there are some network graphs. This one is way too large to see anything at all. Yeah, those are examples that you should try to avoid when you produce your plots. So how to improve your plotting? So the first thing is, what is my message? Define a clear message. And then it's the question, does my graphic really communicate this message? And actually, do you really need a graphic to present it? Maybe not. And you should actually ask yourself, does every line or color I use in my plot really serve a purpose? And you should, in principle, pretend as ink or pixels are expensive. And there are some reading here that is worth considering to look at. This is just a paper, so that's a quick one. That's a book, but it's a quick read, actually. And some simple rules to work with is never use 3D graphics if it can be avoided. So unless you want to be deliberately misleading. So for example, this cone plot is something really horrible because that leaves a lot of questions. What is it I actually see? Is it the volume of this cone, or is it the height of the cone, or is it, what is it? So these cones, they shouldn't be used at all. Pie charts may make sense, but they can be hard to interpret. So maybe reconsider if you when you are talking about using a pie chart. And the background color should mostly be white or almost white. So the light gray is usually not so beautiful to work with. I think that is maybe not always considered in all these plotting toolboxes, is that the plot palettes should be adapted to human visibility, visual sensitivity. So for example, you should think about not using reds and greens and blues. In the sense that colorblind people have difficulties telling the difference between red and green, I think, and they wouldn't see the difference between them. So if you work with these colors, you should at least make sure that there is also an intensity variation in the perception of these. An easy test is actually to print it in grayscale and see if it works. And then use combinations of colors and transparency in a smart way can also help. So for example, this very cluttered plot here, if you would have done that with a central average line and then just transparent band telling about the width, then you would have increased the readability of that plot really drastically. Then some people have put some thoughts into grammar of graphics. So first of all, what is grammar? So it's a set of rules constructing a sentence. And depending on how and they also tell the relationship between how these words actually build up a sentence. And that concept can be actually applied to graphics as well. So we can say that the graphics itself is a sentence, and the different components can be decomposed into grammatically kind of framework. And if you are interested in that, how to build up the graphics, then you can look at the book Grammar of Graphics. And if you look at, for example, this image, you have different components. So this is just an example, a nice plot. And I have already pre-worked it a bit, and you can see that we can divide it into different components. We have one thing is the data mapping. Then we have different points. We have axis and coordinate systems. And then finally, we have labels and annotation. And together, they build up this plot. And that can be done using different frameworks or toolboxes. But in principle, we have here on plots, you need to at least have a curve legend telling what each curve is represented. Then axis labels telling what you see on each axis. And finally, you need a title on the top telling what these are if you have multiple plots in the same figure. Because you want to make sure that people understand what each subpanel actually means. If you work with the images, important thing is to have a color bar telling what is actually the color mapping I'm using and which values are associated with each color. And in scientific context, a scale bar is also really good to introduce to tell the size of the objects you have. The scale bar can also be replaced by having the axis scaled in the right way. So you're not showing just the pixel positions, but you actually show world coordinates, metric coordinates. Color maps, I think it was in the first lecture, I talked about and showed a lot of color maps. And that's also something that people have put some thought into. And this not very well resolved decision map gives you a guide how to select which kind of color map you want to use. And there are different ways to present the data. Here you can see if it's a diverging, multi-sequential, cyclic, or sequential color map. If you have continuous or discrete data, and in the end, it gives you a decision guide to how to select your color map. And what is my message? That is the question what you can start looking at. In this case, I only have some random dots with some trend. And it doesn't tell much if you just look at it. And here I'm using a package called ggplot from Plot9. And that is a system that is working on this grammar concept. So you have, first you do some data mapping, and then you say, you add the information about what kind of points you want to, or how you want to show the data, and that gives you this. Then the next step is to actually, to this plot, add that we have the geometry of points. You want to do some smoothing, and you want to add labels. In this case, I start telling that we have X is weakly correlated with Y. And finally, I also add some color scheme. No, that doesn't work anymore. Yeah, there it is. Color theme. And then it's a question, does my graphic actually communicate the information I want to tell in a good way? And this is, again, some spread random data, and maybe not so well showing what we want to do. We can see that there is some compaction in the middle, but these transparent dots may not be the best way to represent this data. So let's look at a different way. Here I have reduced the data into bins. So it's a kind of a histogram actually, where you can see that there is a trend in the data. So this is some weighted trend. And then you can see also that there is a lot more counts in the middle than out in the corners. That's a way to represent. You can even reduce it even further, just using some isolines showing the intensity of the data. And for doing all this plotting, the standard package that is used a lot is Matplotlib. And there are a couple of good examples. I think this book helps a lot because it gives it in a cookbook way. More or less, you can ask for what you want to do, and it more or less tells you directly. Plotly and Seaborn are some alternatives. And if you want to work with this grammar style, then the ggplot is a way to do that. And to get an overview of all these packages, there is a link here where you can look at what you can use. And yeah, that's the end of today. I talked about a little bit of statistical consequence, not really statistics, because there are many statistics courses out there, and I wouldn't have the time to really go into the depth, but I hope you got the point that the more measurements you do in your hypothesis testing, you need to actually correct for deviations. And sometimes it can be helpful to use simulations for the understanding. And next thing I was talking about was also the data frames, and finally now visualization. And yeah, that was all for today. Next week we have Easter break, so enjoy the mountains or wherever you are going. And after that, I think it's time series analysis that's coming up. So thank you for today and wish you a good Easter.